Hello everyone, this is the third of the three lessons that I have for you on nuclear energy. Previous ones were on nuclear reactions, on calculations for nuclear energy, and this one is going to kind of focus on the Canadian nuclear industry and our Canadian nuclear reactor, which is the CANDU reactor. And that just stands for CAN for Canadian. Deuterium is referring to the heavier version of hydrogen, the hydrogen isotope that's used in the water. And that one is this version of hydrogen here that's used in the water, and it's called heavy water because of that. So that's where the D comes from, and the U for the fuel, which is the uranium. So this one here, this is the reactor that we're taking a look at just a little bit to the east of Toronto in what is called Pickering, Ontario. Sits on Lake Ontario here. So what this is showing is all of these different circular shaped buildings that we see, 8 of them. Those are the actual nuclear reactors, and I don't believe that all of them are functional anymore in Pickering. I think a few of them have been decommissioned. The actual generating buildings, they're tucked in behind the reactors. And this here, if I recall, is a vacuum building. And if there is an escape of radiation, then the idea is a bunch of that will be drawn into that vacuum building. Typically, these reactors do sit on a body of water because you need to have some sort of a cooling mechanism. And what works very well for that is a large body of water. So the map that we're taking a look at here is for nuclear energy, obviously in Canada. We're taking a look at Canada here. And just a couple of things that I did want to point out is uranium, where it comes from in Canada, where it is mined. All of the mines that are currently active are in northern Saskatchewan, and that provides not only uranium for the Canadian nuclear industry, but as we'll see, for many other nuclear reactors around the world. And then just kind of zoom in, and on the next slide, we'll take a look at this again, a map of really central Canada, Ontario, Quebec primarily, because that is where the nuclear reactors are really located in Canada, with one exception, and that one exception is the southern tip of New Brunswick, Point Lepeau. There is one single nuclear reactor there, and that is the smallest of the nuclear reactors. The big ones are all in Ontario. So Darlington, that is where the biggest of the single nuclear reactors are. Pickering, they're sort of in the middle, and Bruce, they're fairly large ones at Bruce as well. So just a single one at Point Lepeau, but there are multiple different reactors at these ones in Ontario. There did used to be one in Quebec as well, but it was decommissioned a few years ago. So now only the 2 provinces in Canada that do have remaining functional nuclear reactors, and they were built many, many decades ago. There have been no nuclear reactors built in Canada for many decades now. The first one, however, does go way back, quite a few years, to 1956 in Ralston, Ontario. That's where the first one was built. They have been built around the world, sold to and built in other countries. So that includes, as I have here, China, South Korea, Romania, Pakistan, India, and also in Argentina. So in Canada, it is now 19 remaining nuclear reactors. Again, there will be multiple reactors at some of these facilities, like Bruce and Pickering, and it accounts for about 15% of Canada's energy production. And obviously, if most of those reactors are in Ontario, that's where most of that is coming from. Most provinces don't generate any energy from nuclear energy. The size of each reactor varies considerably. Again, the smallest one would be just a little bit bigger than this, megawatts, 700 megawatts, and that's the one in New Brunswick. And the bigger ones in Darlington would be up to about 3,500 plus megawatts of energy. So the CANDU reactor is one of the few reactors around the world that uses unenriched uranium. So what that really means is that you can more or less dig it out of the ground and use it automatically in a nuclear reactor, a Canadian nuclear reactor. So uranium-235 is the isotope, which is the only naturally fissionable element. So naturally occurring, natural ore that can be dug out of the ground and struck by, as we'll see, neutrons to get the reaction going and then start to split it apart, the beginning of the nuclear fission reactions. So in the CANDU reactors, The natural resources only have a very small percentage, less than 1%, but that in fact is high enough to be operational in the CANDU reactors. The remainder of the uranium is in the form of uranium-238, and that is not the fissionable form of uranium, so it does have to be separated out. And if you do want to use it in some of the other reactors around the world, it needs to be bumped up in terms of the percentage of uranium, typically between about 3 and 20% in the fuel, and that does require, again, separating out these different isotopes, and that involves using what you may have heard of before, a centrifuge. And if a country does have the ability to enrich uranium, if they do have these huge centrifuges to separate out the different isotopes of uranium, what that also means is they also have the potential to bump it up to a much higher percentage, which can be used in nuclear bombs. So Canada has signed the Nuclear Non-Proliferation Agreement, and what that does mean is that we do not sell uranium to countries where there might be a risk that they're going to use that uranium in order to build nuclear bombs. Canada is the second largest uranium producer in the world. Kazakhstan is the largest producer, and in fact by far. Most of the uranium that we mine is exported, and again, most of it does come from open pit mines, which means you just remove the topsoil, dig down a little bit, and dig it directly out of the ground. There is no deep mining that is necessary. Just below the surface of the earth is where you can find the uranium. So fairly recent data here, this is 2018, and this is across all of Canada. So these are Canada stats. And this is not by province, this is as a whole. So in terms of energy that is used, here we're talking about for the generation of electrical energy. By far, most of it does come from hydroelectric. So huge hydroelectric generating facilities in provinces including British Columbia, Manitoba, Quebec is a huge one, and even Ontario as well. So that's why we see a huge percentage. Provinces like Alberta and Saskatchewan, really minimal input for electrical energy generation coming from hydro. In those provinces, Alberta and Saskatchewan, it's mostly the fossil fuels. So oil and gas, that would be natural gas, methane. From there, coal as well is still burned to generate electrical energy. Nuclear again, 15% across Canada, but that's pretty much all coming from Ontario. So for all of the western provinces, for example, it would be zero in terms of that amount of energy. It's coming from nuclear. Non-hydro renewables, this would include wind and solar energy that would fit into that category. So again, this is across Canada. If we were to take a look at the individual provinces, which we will, and not in this lesson, but in another one, we will see that it does vary considerably from province to provinces based upon the resources that they do have available. And truly what it does come down to is, what is the cheapest way to generate electrical energy? So really nice picture here from Natural Resources Canada, or NRCan. And what I'm going to do is just go out of this presentation just so we can see it in a little better resolution. I already showed you the picture on the right-hand side here, but some kind of interesting information that it does show on the left-hand side that I do want to kind of share with you as well. And also this one here, which is also from NRCan. So I'll just scroll through here. So they have lots of really nice, factual information about the CANDU reactor, and again, where they are located. So you'll notice that it does say here that there are 10 of them that are operational right now outside of Canada. And again, I did say that Canada has signed this non-proliferation policy, which means that it can only be used for the generation of nuclear energy and not for nuclear warfare. Where is it produced in the world? Very recent, 2019. So Canada and Australia, they produce 12, 13% of the world's supply each. But yes, it is Kazakhstan that's producing really almost half of the world's supply of the uranium. In terms of nuclear power, How does Canada fit in the international scale? So again, this is fairly recent data in terawatt hours, and Canada's nuclear power contribution is about 4%. So that puts it, sixth or seventh somewhere in terms of the ranking. U.S. Biggest country in terms of the nuclear power generating stations that they do have there. We already saw this one. And so things do fluctuate in terms of the production of uranium from year to year from Canada, really depending upon supply and demand. So starting at the lower left-hand side here, let's just take a look at some of this data. So again, Canada, the second largest producer in the world. Percentages vary depending upon the source that you go to. So here it says that 80% of our uranium is exported to other countries. 13% of it we use for fuel in our Canadian reactors. So in northern Saskatchewan, big, huge haulers take the uranium ore out of the ground. It does go through some initial processing. So it comes out of the ground in this form here, U3O8. So processing that does take place from this so-called yellow cake. So initial refining into UO3 or uranium trioxide. And then it really depends upon where it's going to be used and what kind of reactor it's going to be used for. So it can be converted into uranium dioxide for our CANDU reactors. For other reactors around the world, in the so-called light water reactors, ours is a heavy water reactor. Light water reactors, they need a different version. So it's converted into uranium hexafluoride, and then it would be exported into other countries. So before we pop it into the CANDU reactors, it is formed into pellets. So that's what it's showing in this picture here. So these fuel pellets, kind of think about it as the end of a pencil, maybe the top 2.5 centimeters or so of a pencil, and it has here a loonie for scale, the size of one of these cylindrical fuel pellets. And what's really kind of interesting is right here. Again, this is the tip of your pencil, the size of uranium, the tip of your pencil. It is the equivalent to 400 kilograms of coal in terms of the amount of thermal energy that it generates. 2.6 barrels of oil, 350 cubic meters of natural gas. So extremely concentrated form of energy that we do have in these uranium pellets. I'll show you another slide of this. They're packaged into these bundles, and then that's what they do slide into the nuclear reactor. So again, it's 19 of them that we have in Canada, 4 different power generating stations, 3 of which are in Ontario. And here it says 7th. The previous picture I showed you, it said that we were 6th in terms of nuclear energy in the world. Okay, so back over to our presentation here. So this is a schematic diagram showing kind of the inner workings, the main details of the CANDU reactor and some other heavy water reactors as well. So again, the heavy water that we're talking about here, the reason why it's heavy water is because it uses deuterium, this form of hydrogen, as opposed to light water, which is also used, which uses this isotope of the hydrogen. So if we just think in terms of the water, this one here, there still needs to be 2 of them with the oxygen, and sometimes we just refer to this as D2O, that is the heavy water, whereas this one here would just be regular H2O. So both of them are used in the CANDU reactor. So the calandria, that is where the reaction chamber is. That is where the uranium fuel is. That is where the reaction, the fission reaction is taking place. And that is where huge, huge amounts of heat are being generated. So what is that heat used for? Well, it's used to heat up water. So going through this chamber that we do have here, so we have a heavy water moderator, and what this heavy water moderator is going to do is it's going to have an influence on neutrons. So neutrons do have to strike the uranium, but they need to be going at the correct speed. So the heavy water moderator is going to in fact slow down the neutrons. So it's going at the appropriate speed to strike the uranium and cause the fission of the uranium. So that's one role of the heavy water. We also have the heavy water through these pressurized plumbing tubes here. Heavy water has a higher boiling point than regular water, and especially when it's pressurized, and that is somewhere around 300 degrees Celsius before it's converted to a steam. So we have the heavy water in these tubes that's close to 300 degrees Celsius, and it remains liquid. So after it removes out of the reaction chamber, again, it's very, very hot. We'll call it somewhere around 300 degrees Celsius. And then that very heavy liquid water then goes into this chamber here, which contains just regular light water. So regular water at 300 degrees Celsius, it is going to, well, boil, and it's going to convert that liquid into a steam. So what we do have here is steam that is generated. Steam, very, very high kinetic energy. It's going to expand, it's going to create pressure, and that pressure is going to drive it through these really, really huge diameter plumbing pipes, which have light water steam. So where it is going is to the turbine station, where there are these massive, massive turbines, and we're talking several meters in diameter, and steam is going to turn these steam turbines. Connect that to an electrical generator, and that is how we produce AC current, alternating current. That's how we produce electricity. So eventually we just want to return that water back to this chamber here, but we need to cool it off first of all. So that's the idea behind having it close to a lake or a body of water. So you can cool off that light water, return it back to the liquid form. And of course, what that does involve is some warm water that's going into that lake, and that's one of the negative implications with the nuclear energy, is it can lead to the warming up of the body of water and an impact on the ecosystem where that water is seeing an increase in temperature. So the picture that we're taking a look at here, this is a fuel bundle. And we can see someone that's holding the bundle here to kind of get an idea of the size of it. Think about a fireplace log. That's about what the size of it is. Only this log here would be enough for a house to provide enough electrical energy to last for 100 years. Is that impressive or what? One log in the fireplace, enough electrical energy, enough energy for that entire house for 100 years. So a bunch of these bundles, they slide into this here, and we can see sort of the scale of this. Someone that's standing here, it's on these big sort of railway track guides that we have, and that's going to slide into the calandria of the reactor, and that's where the reaction is going to take place and where the heat is going to be generated. So this is showing, again, the calandria here. This is showing the tubes that we have, fuel rods that slide in, and these fuel rods are made up of those fuel pellets. And again, these are cylinders, and these cylinders are really about 2.5 centimeters high, and their diameter is about 0.5 centimeter. And remember that one of these is the equivalent to 400 kilograms of coal, and this literally does weigh just a few grams. So extremely concentrated energy source that we do have. So what's going on overall? Well, I already mentioned a little bit about this. So overall, it is fission. This is a fission reactor. All of the nuclear reactors that we do have around the globe, they are fission reactors, and they release heat. This heat energy is used to, doesn't sound all that fancy, boil water is what we're doing. And that high pressure steam is going to turn the turbines, connect it to an electrical generator, and that produces electrical energy. In fact, this is almost identical to the process that takes place in a coal or oil or natural gas electrical generating station. We're using that fuel to generate heat, boil water, create steam, and turn turbines as well. So the core of the reactor is where the uranium is, and that's where we need to bombard it with neutrons in order to initiate and continue the fission reactions. So this reaction, we've seen this one here before. So what we have is our very large mass, I'll just call it big, uranium. It's fission, so we split it into things that are smaller. And not only that, what has happened is that we lose mass. Where does that mass go? It goes into energy that is released in this process. And to make it a little bit more visual, and just to show that this is a chain reaction, so the neutron has to strike the uranium, splits it apart, but now notice that we have more neutrons that are also formed that can in turn strike more uranium, and this just continues and continues through this chain reaction. Of course, you need to control this chain reaction. So the heavy water moderator is going to ensure that all of these electrons are going at the proper speed. And we also don't want the reaction going too fast. So sometimes we need to be able to remove those electrons so they're not striking the uranium to slow down the reaction. And that's the idea behind this picture here, and something that are referred to as control rods. So either slide them down to absorb the neutrons, slide it up to not absorb the neutrons, and increase the rate of reaction within the calandria. So heavy water, again, the D2O is a moderator, and what it really does is slow down the fission products, the neutrons, so they can strike other uranium and continue with the chain reaction. All of it is controlled, the rate at least, by these control rods, as it's showing in the picture here. Heavy water is also a coolant. So in addition to, well, not only a coolant, but it's going to transfer the heat. So in addition to acting as a moderator, we saw this before, what's going through all this plumbing here is the heavy water. And then it's going to lead to the boiling of the regular water or light water inside of this steam chamber here. So much of this we've seen before. Once we have the high pressure steam that's going through the plumbing, we can turn the turbine, which in turn connects it to an electrical generator and allows for the production of electrical energy. So this is one of these turbines that's in the process of being assembled in a nuclear generating station. So the size of these, again, the scale is absolutely massive. And what is turning these is steam, high pressure steam that's created from the boiling of water. That's enough to turn these massive, massive blades. And again, the scale of these from the top to the bottom, we're talking about several meters, like 3 to 4 meters in size, and there will be one or more of these associated with each one of the reactors. So in terms of the safety, the CANDU reactor is recognized as one of, if not the safest nuclear and most reliable nuclear reactors in the world. In fact, I thought I just read that one of them just set the record for being in service the longest without being decommissioned or without having to undergo any significant maintenance. So it is impossible for a nuclear explosion to take place at a CANDU reactor simply because it is using unenriched uranium that is only 0.7% fissionable material, and you cannot have a nuclear explosion with that percentage. So no chance of that, but there is high energy ionizing radiation. So we've talked about different kinds of EMR. So here we might be talking about radiation on the order of X-rays and even gamma rays, which are of course extremely dangerous to us and other biological organisms. So that does need to be contained to prevent it from escaping into the surroundings. So there are, yes, surrounding walls, very, very thick surrounding walls of about 1.3 meters of concrete, which does prevent the loss and the escape of this radiation. The fuel, after it has been converted, after the uranium has been used, there is still a lot of energy in the fuel, and but it can't be used in the reactors that we have available right now. So in that spent fuel, the spent nuclear fuel, it does remain radioactive and it does continue to emit electromagnetic radiation for a long time, like about 1,000 years before it's actually safe to be around and safe to handle. So this is one of the major concerns, is how do you deal with the spent nuclear fuel? Having said that, in Canada, even though we've been doing this for 50 or 60 years, there isn't a lot of spent fuel that we have. This is what they do. First of all, this looks like a big, huge swimming pool. This is the way that they store it, underneath a few meters of water for about 1 year. This is when it is the most reactive, after taking it out of the calandria. After that, they will remove it out of this water bath that they have, and they will put it into solid, for the most part, concrete containers. And these, at this point in Canada, are stored on site at the nuclear facilities. So Darlington and Bruce and Pickering, for example, is where they do have the spent fuel stored within these concrete containers. Eventually, the plan is, though, we need to store it for, well, maybe 1,000 years. So the talk is underground. So here it shows about 500 meters, 500 kilometers underground. And this could be anywhere in the Canadian Shield. So it can't be in sedimentary rock like we have in Alberta and southern Saskatchewan. It does need to be Canadian Shield, so central and eastern Canada, more of a solid rock. So deep, deep, deep down below the surface is where the talk is of storing this over the long term. And there already are some deep mines in places in Manitoba, even though they don't mine it there, even though they don't use it there. In a place called Flin Flon, Manitoba, is one of the places that they have been talking about for storing underground for a long period of time the spent nuclear fuel. So just a few of the safety features that are associated with the CANDU reactor. So as soon as you have light water that floods the calandria, it doesn't work anymore. You need the heavy water to slow down the neutrons, so that would shut it down. So if you allow light water to come in, that'll shut it down. If you allow heavy water to go out, that'll shut it down. So many, many different mechanisms to automatically shut down the reaction from taking place. Control rods, they drop down. There's also, again, I mentioned the 1.3 meter thick containment walls. I pointed out in the initial slide that vacuum chamber, which will suck out any radioactive elements that might be released. And so the entire thing takes about 2 seconds to shut it down. So very, very safe CANDU reactors that we do have. So why use nuclear energy? Well, as we already know, it produces mind-boggling amounts of energy compared to other energy sources. So it is about 3.7 million times more energy for the same amount of coal. There are no emissions like SOx and NOx, and recall that those are responsible for problems that we have with acid deposition. In Canada alone, this would eliminate, well, more than 100 million tons of carbon dioxide, the major greenhouse gas, of course, responsible for human-induced climate change, global climate change. And greater energy reserves. We do have a fair amount of uranium, even though both fossil fuels and uranium, they are both non-renewable resources. And again, what that means is we will run out eventually. We still have fairly significant reserves of fossil fuels, but again, huge problems associated with the burning of fossil fuels, the CO2, the NOx, the SOx, that does go along with it, particulate matter in the air, and probably a number of others. Although we do have a lot. For uranium, though, we have even more. Are there environmental concerns? Yes, there are, but probably not as significant and severe as what we're encountering with the fossil fuels. So what about the other side? Why not use nuclear energy? Well, yeah, so it is non-renewable. So it's not going to be in the next year or decade or two, but eventually we will run out of the fissionable uranium. It does produce radioactive waste, and that of course is a concern, especially because it remains hazardous for hundreds and possibly thousands of years. It is an enormous cost. This is why we're not building them anymore in Canada. The cost associated with them does run into the billions of dollars. I'm going to say somewhere between $3 and $5 billion per nuclear power plant. And then on top of it, you need to operate it. You need to prepare funds to store the fuel in the end. And if something does happen, you need to prepare for this as well. What do you do if there is an accident and the cleanup after that accident? Uranium, of course, can be used for other things, so that's also a concern for nuclear weapons. So even though Canada doesn't enrich the uranium, we do need to be extra careful who we are selling our uranium to. Those that have not signed the Nuclear Non-Proliferation Treaty, we would not sell uranium to those countries, as there might be a risk that they would enrich the percentage and use it in the development of nuclear weapons. And I mentioned with thermal pollution in particular, we're talking about bodies of water that are associated with that nuclear power station and the cooling off that is necessary in order to cycle that light water back into the reactor and continue the process.